So y'all have a card in front of you, want to collect some information. So write down the name you want me to call you, not your like name that's on, your birth certificate or whatever. Because that's how I'll write you in my grade book. And if you put like your first name, then I'll be like, who the heck is William? I don't know who that is. So put that down. You can tell me your pronouns if you like. Tell me what lab you're in. If you're not in lab, just put no lab. Tell me your major or area of interest. If you are pre-health of any kind, nursing, dental, vet, medicine, make sure you write that down. We try to identify those students early so we can make sure you're aware of resources that are available to you. If you have conflicts, I've already gotten lots of things about athletes with various lacrosse and volleyball, and I don't know what all else I've gotten. But go ahead and tell me what sport you're in, and that way I know to be paying attention to those, because sometimes they'll put out an announcement for, bass fishing, but I don't have any bass fishermen, so I can just ignore that. So make sure you let me know what sport you're in. You might have other conflicts. If you know, like my sister is getting married on March the 3rd and I just can't be here, the 2nd, 3rd, or 4th, let me know that too, so that we can kind of plan ahead. If there's something going on that day, I can make sure you have the materials ahead of time. And then if you have any concerns, if you are somebody who gets really bad test anxiety, I can maybe give you some tips on that. If you have like some need of accommodation, or you need to know how to get accommodations, that might be something you want to let me know about. If you really struggled with chemistry last semester and you're concerned with being able to keep up, that's going to be something I want to kind of keep an eye on for those kinds of things. Anything at all, maybe it's just, like I have a tendency to pass out if you say the word blood, and then I'll avoid saying the word blood. Nobody passed out. Excellent. So, I do have one conflict. Next Friday, I will be at a conference. I am planning to have our first quiz on that day, but that is the only thing we will do that day. So it won't be a full class. You'll just come in, take your quiz, and when you're done, you can leave. So I'll give you more details on that next week. So last thing that you're going to put on there is the dead person you'd like to talk to. It cannot be somebody who is currently alive, but any person you want, and we're going to assume through the magic of a hypothetical situation, you do not have any problem communicating with this person. So if they are mute, if they don't speak the same language as you, you can still understand. So who would you like to have coffee with, get dinner with, just have a phone call with? So, all right, for pre-health people, a lot of people in this class tend to be pre-health. There are 2 summer programs that you should be aware of, primarily because they are both free. So it doesn't matter how rich you are, you can participate in these programs. They provide the housing, they provide the meals. All you got to do is show up. All right, questions. So we are diving into section 6.5 today. On Monday, we're going to do section 7.1 and 7.2. So I highly recommend that for Monday, you take a look at section 7.1 and 7.2. Today, we're looking at 6.5. Okay, so just a few reminders from our last chapter. We were looking at how the electrons fill into the atoms. And so remember that, I'm going to kind of sketch this down here, that we can kind of think of there being layers. Shrek says that odors have layers. Well, atoms have layers too. In our first layer, we can hold 2 electrons. And then in our second layer, we can hold 8, but those 8 kind of come in sets where we have some s electrons and then these p electrons. And that's how we end up getting the formation of the periodic table, is from that layer. So each atom has one extra electron, and we call this section here the S block, right? There's these two columns. This section here we call the P block, and this section here we call the D block, and then down here is the F block. And what we mean by that is that as we add electrons, that's the kind of electron that, excuse me, that is last being put in there. When we write the electron configurations, we can write out all the electrons, but it's usually easier to do what's called a noble gas configuration. So we look at the last noble gas before that element. So if it's element 12, we would find that neon is the last noble gas before that. We put that first, and then we just write the outside ones. What's the word for the outside electrons? Valence. Okay, so that's a good word to know. Valence electrons. And the ones that are included in the noble gas configuration, what are those electrons? Those are core electrons. So we have valence and core electrons. All right, so for this, whatever row we're in, the last electron, zoom in just a little bit so you can see this tiny step, would be NS1. Here, our configuration would end with NS2. So N would be 1 if I was doing hydrogen, N would be 3 if I was doing sodium. If I'm all the way down at cesium, that would be 6, right? And then over here, I would have NS2, because I didn't lose those electrons, but I would have NP1, NS2, NP2. I'm going to skip that so I have some room. NS, NS2, NP4, and then over here, NS2, NP6, okay? So remember writing our configurations. If I were going to do, let's say, this element here, which would be chlorine, then I would look to the element, chlorine. The noble gas before it is neon, so find that. And my configuration for chlorine would be neon, which would go in square brackets for chlorine. And then in this column here where chlorine is, I would do N. N is the row that we're in. So this is row 1, 2, 3. I'm not counting how many are in the column with chlorine because that skips a row. So I'd start over here, 1, 2, 3. So this is 3S2. And then counting over from here, 1, 2, 3, 4, 5. 3, 2, 5. Outside of the noble gas configuration, I have these electrons. So I just look at the superscripts, the little numbers that are up higher, and that tells me how many valence. So there are 7 valence electrons. That's going to become important in chapter 7, knowing how many valence electrons there are. All right, other things we need to know about the periodic table. What's special about this diagonal area here? James, you have a thought?
Doesn't it separate metals from non-metals?
It separates metals from non-metals. So over here, we have non-metals. And really the only non-metal that isn't in this corner is hydrogen. So I call hydrogen our problem child because pretty much every rule we have, hydrogen's like, except not me. Okay, so our non-metals are over here, and then all the stuff over here are metals. And then these ones that are on this straight line, and then a couple that are just below the line. So you can see the brown ones here, germanium and antimony. These are what we call semi-metals or metalloids. Just kind of letting you know that there is a rationale for why we call those semi-metals rather than saying they are in another category. Why do we care about metals versus non-metals? They bond differently. So chapter 7 is going to be all about bonding. And one of the first things that we're going to be talking about is ionic bonding, right? So when they form ions, what kind of ions do non-metals form? They form anions. So over here, non-metals form anions. So think an is like anti. Anions are negative. So I really shouldn't ever see an oxygen plus. Now, there are always exceptions, but for general chemistry purposes, I shouldn't see oxygen plus. In contrast, the metals form cations, and those are positive. So we have the metals versus the anions. What we're going to be talking about in section 5 is some properties that are periodic, which means that instead of them constantly increasing or constantly decreasing as we go through the periodic table, they go in one direction and then they reset at the beginning of each row. So if we think about comparing the atomic number to the number of protons, the higher the atomic number, what happens to the protons? There's more, right? Because they're one and the same. So it constantly goes up. We're going to look at a handful of properties, 2 real important ones, but 4 overall that kind of reset as we go through. So the first one is going to be size. And so we'll talk about why this happens, but first I just want to get the trend down. As we go down, what happens is totally expected. So I'm going to go down this size, radius, increase, or size is going to be determined by radius. Now, there are several ways we can determine what a radius is. We'll talk about that later. But as a general rule, the more layers it has, the bigger it is. That's not surprising. What is surprising to people is that this isn't a trend that goes in along with the atomic number. It's not every higher element is larger. So if I go this way, the radius decreases. So if I compare hydrogen to helium, helium is smaller than hydrogen. Okay, that's a counterintuitive thing. So you kind of have to force your brain to reckon with that. Otherwise, your brain is just going to keep going in the wrong direction. Lithium is much larger than fluorine. In fact, even though we reset as we go across the row, so that it gets smaller, 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 and then when we add the new layer, boom, it's bigger. Smaller, 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 boom, it's bigger. Keep doing that. Lithium, as a neutral element, is still larger than iodine. So even though iodine is element 53, lithium is element 3, lithium is still bigger. Okay, so that's how exaggerated that trend is. Now, there are going to be exceptions to trends. We're not going to worry too much about the trends in size. Most of those exceptions are in the transition metals, which we kind of ignore in this class. So for the what we call the main group, the S and the P block, the main elements that we worry about, that trend is pretty consistent as we go across. All right, the next trend we are going to look at, so we looked at radius. We're going to look at metallicity. Metallicity is tied to radius. The farther away the electrons are from the nucleus, the easier it is for them to move around. So if I have a really big element like lithium, those electrons can travel from atom to atom pretty easily. So as I have an increase in radius, I also have an increase in metallicity. As I have a decrease in radius, I also have a decrease in metallicity. So basically, our trends are going to go along this diagonal. Okay? So in the case of radius and metallicity, we increase to this point. Okay? We should have really good conductivity for barium, rubidium, those kinds of things. We should have very poor conductivity for things like fluorine, which is a gas, so can't really do that. But even sulfur, not so great at conductivity. All right, so those are trends that increase down and to the left. Our next 2 trends are going to go in the opposite direction. Ionization energy is taking an element, so I'm just going to call it E as my element, and turning it into the positive element and an electron floating away. And that's ionization. Doesn't take much for a metal, and that's why they form those positives very easily. It takes a lot of energy for the non-metals, that's why they don't work. Okay, so the farther away something is from the nucleus, the easier that electron is to take out. So if I get really small atoms over here, they're really close to the nucleus, those electrons. So those electrons are harder to pull out, so the ionization energy pulls off. So ionization has to do with taking away an electron. Even though we can form an ion by adding electrons, we call that electron affinity instead of ionization. So ionization energy is pulling the electron away. So that increases as we go across. It also decreases as we go down. Now, there are more exceptions to ionization energy than there are to the radius, and we will talk about some of those because those appear at specific points in these main groups. We'll get to that in just a minute. Then the other thing that is going to be very related to bonding is electronegativity. Put down here, electronegativity, how attracted electrons are to an atom. And here's the key thing. In a bond. Okay, so we talk about electronegativity when it is bonded to something else. For this reason, in general chemistry books, we tend to ignore the noble gases because for noble gases, we say, well, they don't like to form bonds. The truth is, all the noble gases have been shown to form bonds except helium and I think neon. I don't think they've yet formed any bonds with neon, but argon, krypton, and xenon can all be forced to form bonds. They follow this trend exactly the same way the other things do. But what we normally say is that for electronegativity, fluorine has the highest. Okay, so along this yellow diagonal here, this is fluorine. So if we ignore the noble gases, fluorine is in this upper right-hand corner. And so what we can do is if we're comparing electronegativity, we can say, how close is that to fluorine? Okay, so if I'm comparing carbon, here's carbon, nitrogen, and oxygen, and I say, is carbon more electronegative or is oxygen more electronegative? Well, I'm going to say, well, which one's closer to fluorine? Oxygen is closer to fluorine, and therefore it's more electronegative. If I go down, then it's kind of the same thing. So this has the highest number for electronegativity is 4. Fluorine is a 3. So if I'm comparing bromine versus iodine, bromine is more electronegative. So it drops off by about half as we go backwards. So 4, 3.5, 3, 2.5, blah, 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 and we go backwards. But there's a big jump here. Okay, going down, it goes 4 to 3, and then they're smaller. So going from this row 2 to row 3, there's a big jump, and then it's smaller. So what about hydrogen? Hydrogen has an electronegativity that sits right about here. So between boron and carbon. So it's not really behaving like it belongs over with the metals, but it's not quite behaving like it belongs over with the halogens. You have an assignment on Canvas. This assignment is due on Sunday that goes through these trends. We have about 10 minutes, so I'm going to go a little bit quick here. So you're not going to be able to write everything down, but remember these PowerPoint slides are on Canvas. Okay, so the reason that these periodic trends exist is because of the electronic structure. Remember, we said that within those columns, they had the same configuration. The only thing we were changing was whether it was 2s or 3s or 4s, right? So we are looking at those outside electrons called the valence electrons. The properties, that are related. We looked at atomic radius, and so these circles are drawn to reflect the size. So you can see the smallest ones are over here, and the largest ones are down here. This is lithium here, and it's a little bit larger than iodine over here, okay? So that general trend of getting smaller as we head up towards fluorine and helium. All right, so if we were to look at a graph of this, remember that if we do atomic number versus protons, we just have a straight line going. But this is something that it goes in one direction and then it either jumps up or it drops down. So in this case, we go down, 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 and then jump up, down, 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 jump up, down, 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 jump up. And so in the transition metals, there's some exceptions, but we're not worried about it. So the biggest ones are Li, Na, K, Rb, Cs. What is the name for those elements? Group 1, and do we have another name for it? Alkali metals. Okay, the largest element in each row is the alkali metal. The smallest one is the noble gas. Those are key things to remember. All right. Some subtlety here. The biggest change is early on. So notice that as we go down, we get this big drop, and then it's more of a subtle change. Big drop, and then more of a subtle change. Okay. So that's some little nuance there, which means that yes, carbon is bigger than fluorine, but not by a lot. Carbon, nitrogen, oxygen, fluorine, they're pretty similar in size. All right. See, we kind of went through that. Why does this happen? Okay, this has to do with the nuclear charge. So nuclear charge just means how many protons there are, Z. When we have hydrogen as an atom, that Z plus 1 is entirely felt by the electron over here. If I had a helium plus, now we know that doesn't like to happen, this electron would feel a 2 plus. Okay, and this electron on lithium, if there was only one electron, would feel a 3 plus. Okay, so since there is a stronger positive charge, that electron gets closer and closer and closer. The larger the nucleus, the more protons in the nucleus, the closer those electrons get in. Okay, so what we do when we look at our electron configurations, remember when we were drawing these things, the orbital configurations, the lower down these are, that means the more stable or the more negative energy. So if I were to draw this for, let's see if we'd have another one here. If I were to draw this for carbon, it might look like this. But if I were to draw this for fluorine, it would be a little bit lower. Okay, so that the lower down these lines are, the closer they are to the nucleus and the more stable the orbitals are. Stable means that the electrons are likely to stay there, which is where the Aufbau principle comes from. Remember, Aufbau said, put the electrons in the lowest down orbitals first. Those are the most stable ones. So that's why the electrons stay there. So key thing to remember, because this keeps coming back in chemistry, more stable is favored. We like that. More stable is closer to the nucleus. All right, but every atom actually has more than one electron. We have, instead of the electrons seeing all of that positive charge, they only see some of it. They're being blocked by the other electrons. So we talk about what's called the effective nuclear charge. So sometimes this is written ZEFF. So the EFF is effective. Sometimes it's written Z star. Okay. So what that means is, if I am that last electron in lithium, so remember lithium has 3 electrons, that last electron is on an outside ring, and there are 2 electrons that are between that electron and the nucleus, right? And so it'd sort of be like on a hot summer day, somebody's got like an air conditioning unit right here, and Maureen over here wants to feel the air conditioner, but these 2 people are in front of her. So she doesn't get the full effect of that air conditioner. Okay, so our effective nuclear charge is less. Okay, it goes down. So we can see that if I have 2 electrons, these 2 electrons, they're going to try and get away from each other a little bit. And if they get closer to the nucleus, they kind of have to get closer to each other. So that's a little bit of what we call shielding. But more shielding happens when we have layers. Okay, so these do a bit of shielding, but not much. But if I go to having that lithium, oops, I thought I had the picture for lithium. If I have a third one, then it has more shielding there. Okay. So what happens is, as we move across the periodic table, the nucleus has more positive charge, so the element is getting smaller. There are more electrons, but they're not blocking each other too much. But once I create a new layer, that outside layers blocked a whole bunch, and that's why the atom gets bigger. Okay, ionization energy. We talked about, this is what we mean by ionization, is that we're taking away an electron. Notice from our graph here, the trend is in opposite direction. So now our alkali metals are on the bottom and our noble gases are on the top. So the lowest ionization energy is for group 1. And the highest ionization energy is for group 18. So that's the kind of question I might ask you on a quiz or a test. I might say, in row 2, which element has the lowest ionization energy? So you would think to yourself, lowest ionization energy is in group 1. So we go over, and lithium is in the second row. So lithium would be the answer. In row 4, what element has the highest ionization energy? We're going to go down to the row with potassium, but highest is over by the noble gases. Krypton has the highest ionization energy. All right. I'm going to skip this for now because this gets a little complicated. Maybe it'll be easier if I do it this way. Look for what I'm looking for. I don't have the picture in here. Okay. So I'm going to stop with the PowerPoint and with my last minute talk about the size of ions. If I have a lithium atom, I have lithium with its 3 protons here. I have 2 electrons here. And then I have another electron here. If I take away that electron, the size of the atom is kind of determined by how far out this electron goes, right? So if I take away that electron, what happens to the size of lithium? It gets smaller, okay? Cations, positive charges, are smaller, a lot smaller. Now, in addition to having lost that ring, also, I now have 3 positive charges pulling on only 2 negatives. So they're pulling in tighter. So this ring is even closer than it was before, okay? If I have fluorine, and I'm not going to draw it all out, and I add an electron, so it becomes negative, now those electrons are pushing away from each other, and they get a little bit wider spread. Anions are larger. Now, since I'm not changing the number of rings, they don't change size a lot, but cations are a lot smaller. Okay, so that should be enough to get you through your homework assignment. And we'll talk about the exceptions to ionization energy on Monday.